So my name is Christian. I'm a software architect with Intel. I'm working for Intel DPDK since DPDK actually started a number of years ago. Very grateful for the guys to inviting me to have this session here. I think I'll also invite Damian to co-present if need be, and so that maybe we can use this session to level set everybody on how we use DPDK and what's the basic setup here. And maybe we can solve some of the questions. We can go into the next days with the
basically, my idea is to jump
level
in
set.
and explain
Yeah.
how we use the particular section Christian is talking about in specifically in the VPP. So,
Yeah.
yeah.
Okay, so I think it's a pleasure to talk about DPDK at this point. It's a mature project. So maybe let's do it this way. Who in the room actually uses DPDK? Anybody?
At this point, anyone who ran through the thing earlier has used it.
Okay, so that's kind of a bit tricky. I don't want to just say things that people already know, and I don't want to just steal time for nothing. Next question maybe, who sent a patch to DPDK? Who contributed to DPDK so far? Okay, so not that many people, but hopefully more of you will contribute going forward, which I hope it's the same for VPP as well. So DPDK basically just an introductory slide. It's an open source project. It's a fully open source project. Nothing is hidden. Everything is on the internet on dpdk.org. There is a strong, vibrant development community at this point. So you see, like on the right-hand side, a lot of the companies that are actually contributing, active contributors to DPDK. Many of you in the room are part of one of those companies. You probably know that, we do have regular releases, and that includes source code, includes documentation, so on and so forth. It also comes with the validation cycle, of course. Number of committers is growing by the day. Community is growing, which means that the project is a very healthy project. We also started using the Ubuntu convention for the releases. So now we are preparing for release 16.4, which hopefully will be April this year. So this month, actually. Now that's also a dependency for our VPP folks who have their own release 16.6 based on DPDK 16.4. So no pressure. Initially, it started a number of years ago. From the very start, it was BSD license. So the code was donated to the community. But initially, it was just Intel CPU architecture which was supported. And it worked only on some of the selected Intel NICs, like the newer NICs at that point, maybe not that new at this point. So we started with 1 gigabit Ethernet NICs, with 10 gigabit Ethernet NICs, the famous Niantic NIC that you guys know about. Now we got the 40 gig NIC. Along the years, we opened up gradually, and as now we are a fully open source project, we are also multi-architecture in terms of CPUs. And we are also supporting a lot of NIC architectures as well. So it's not just Intel. We have folks in the room from Cavium. In terms of CPU architecture, we have support for Power architecture, IBM Power architecture. We do have support for Cavium, for ARM version 7 and ARM version 8 CPU architectures. Support for Tylera architecture. In terms of NICs, we have NICs from Intel, NICs from Broadcom, from Neutronome. Neutronome is like a system on a chip. Mellanox, Chelsio, whatever. So this list is growing by the day. And Cisco as well, yeah, of course.
Yes, thank you.
So these are the physical NICs, obviously. We also have the virtual devices. So we'll just go on the next slide. So the intention is to have this slot to be a very open, informal session. So I mean, the whole purpose is for you guys to maybe ask questions and level set, ask any things that are not clear now, so that in the next few days of the training we don't have to answer the same basic questions. That would be great, I think. So this is like an overview of what DPDK is. All these libraries that make up DPDK. So what exactly is DPDK? So maybe that's a question for the people in the room. I mean, I can offer you my own perspective. In my perspective is like a set of libraries that we use for to accelerate packet processing, mostly data plane applications on multi-core CPUs, right? I think some people would say common off-the-shelf hardware. I mean, it's not very specialized hardware. It's like hardware that is hopefully as generic as it can be, and as available, as pervasive as it can be, so that you don't need to use as much specialized hardware as we tended to use before. So that's my interpretation. That's my perspective of what Intel DPDK is. Maybe some other people in the room have a different perspective. Like maybe you want to share what is DPDK for you. How do you use DPDK? Any takers? Any people that want to?
Well, I can certainly say how do we use DPDK?
Yes.
And this is quite a good slide to do that. So let me interrupt you quick. So what we use is, of course,
stealing my next line.
Yeah.
But go for it.
Yeah. So we are using core infrastructure beside rings and timers. We are using more or less all the drivers. Some of that are maybe not enabled and they will not show up because the PMD is not loaded, but it's just a few lines of code to basically enable them. So more or less all the drivers. We don't have crypto stuff yet. We plan to do it. And we actually have the crypto, we have IPsec data plane. We would like to use acceleration cards for a data plane. And then on the top, we are quite bad, so we are not using classify stuff. We are not using extensions except the vhost and the KNI. And we are not using QoS, and we are not using packet framework. Okay?
So we're done. We can close this session. Okay. So maybe now we can take it a bit slower, because actually this is one of the points that I wanted to make as well. So I love you guys for using DPDK, but and obviously I'm very glad that I mean at the very foundation of VPP, one of the technologies that enables VPP is DPDK. But I don't love you that much for not using some of these things in DPDK that are, I would say, with a bit of sadness, are my babies, you know. I mean, personally, I looked on some of, I worked on some of these components from the very inception of DPDK. Personally, I didn't work that much on the Polmo drivers, which is actually the core of what you use. So just going back, rewinding a bit slower, what Damian said. So there is, first of all, this layer that is part of Linux kernel, right? Which is enabling some of the setup here. So you guys don't use this. You don't use KNI.
We have support. It may be that this current state of the code is not functioning well. Maybe needs some cleanup because in the meantime we did some big changes in the DPDK code, in the code related to DPDK, and it's just not tested. So yeah, it's there. It needs to be tested. Possibly some fix will be needed.
It requires an out-of-tree kernel module, KNI, so that's an issue for us. some
Yes.
people.
So from the distribution point of view is also creating a problem as well. Yeah. Okay, so maybe start from this side of here. So these are the core components, things that are, let's say, represent the plumbing of DPDK and plumbing of sending packets from A to B, packet reception, packet transmission, right? So EAL is environment abstraction layer. It's like that component that will give you the setup. MBUF is basically the format of the packet descriptor. I think that's pretty fundamental to any network stack, and every time you need to migrate to a different network stack, this is one of the fundamental problems. You have a different format of the packet descriptor that you need to adapt. Sometimes you can adapt easy from format A to format B. Some other times it's not that easy to do that. Mempool is the library for creating buffer pools. So we don't use malloc for runtime packet reception, packet transmission for performance reasons. All the packets have a fixed size, or unless you use we talk about jumbo frames. But anyway, this is like one of the classical ways to do memory management for packet processing. You are going to take a big chunk of memory, you are going to divide it into slabs. And each slab is going to host a packet. Whether it's a 2 kilobyte slab or a 4 kilobyte slab, depends. In that slab, you are going to keep the packet itself. You are also probably going to keep the packet descriptor. Which is basically metadata, things that come with the packet but are not actually sent out on the network interface. They are part of the processing of the packet, the temporary stuff. Ring is the library for basically lockless queues of messages, lockless queues of packets that you send between threads, between cores, between parallel entities here. A message could be really a message, or it could actually be a packet. It could be a pointer to a packet. So these are kind of the fundamental components. EAL is responsible for the setup of the platform, really. So initialization, really. So what you have in here, you have to understand your platform in terms of CPU. Like how many cores do you have? How many CPU sockets do you have? How many cores? How many of them are physical cores? How many are logical? What's the setup there? Obviously, since we are running in user space, we don't have to go and do that investigation in BIOS. We can simply rely on what Linux kernel tells us as part of the file system. So that's why our job is much easier at this point, because Linux kernel does a lot of work for us, right? And the BIOS as well. What other things do we need to initialize or be aware of? Definitely memory, right? So how much memory do we have? How much is attached to each socket? Why do we need that? We need it to allocate packets. So to create the memory pools, the mempool component over here. And also all the data structures that you need to allocate, you have to store them somewhere. So for the purpose of setting up the memory pools, we use the huge pages. This is a hardware mechanism that is part of the CPU, at least part of the Intel CPU architecture. Why do we need huge pages? Is to avoid TLB thrashing. TLB stands for table look-aside buffer. So basically, that translation of virtual address to physical address, that happens every time your instruction actually uses an address. That happens a number of times per packet, or it happens at least one time per packet. So you guys know the story about the paging architecture of the memory. So basically, within the CPU, depending on the page size, the default being 4K, other page sizes which are called huge are 2 megabyte or 1 gigabyte. You have a number of entries, a number of page addresses that are cached within the CPU itself. So Obviously, like if your page is 4 kilobyte, that would store just one buffer or 2 packet buffers. So every other buffer you will have to, or probably even every other packet you will have to use a different entry in that list. And I think that is limited. That cache is limited to 128 entries for 4 kilobyte pages. So then you'll pretty much run out of TLB entries very quickly. So this is why the hardware guys invented the huge pages. So then on 1 gigabyte huge page, you can store even the entire memory pool using just one page. So you'll never run out of TLBs. You'll not get into this issue of TLB misses. Right, so that's why we need to use huge pages. It's a hardware mechanism. We need to discover them as part of EAL. We need to create them. We need to do all the necessary housekeeping to maintain these huge pages going forward. So that's what EAL is also doing. The other thing that we need to use here is probably to discover the NICs. What NICs do? What physical network cards do we have? What manufacturer, so on and so forth, how many ports, are they 1 gig, are they 10 gig, where are they physically attached to which CPU socket, so on and so forth. And this is also what EAL also does. These two kernel modules, IGB-IO and VF-IO, are responsible for enabling the poll mode drivers, which is the key component in DPDK. So as the driver is running as part of user space, you need to access the registers of the NIC. Any driver would actually write to the NIC registers, right? That are part of the hardware NIC, are documented in the specification of the NIC. In order to access those registers from user space without going through system calls to kernel space, you need you simply access the PCI address space, and then you have the standard feature in Linux kernels, which is at this point is pretty standard, IGB and VF-IO, to export those registers, make them visible to user space so that the driver can access it directly. So that's what EAL is doing. These are, as Damian said, the core components, things that are responsible for the plumbing of the system. Then you have the poll mode driver. This is what everybody knows about DPDK. What DPDK is, if you ask people, what is DPDK enabling you to do, is it gives me a driver for the NICs. It gives me a user space driver for my NICs. What is a poll mode driver? Is one of those drivers that work in polling mode. What is polling mode? So it's as opposed to interrupt mode. As we also discussed earlier, we are currently working to enable interrupt mode in our poll mode driver. So basically, we are polling for packets repetitively. This is part of, from the software perspective, it's a thread that is doing that. From performance efficiency reasons, we tend to affinitize, we tend to map a single software thread to a hardware thread, and that hardware thread sometimes is a hyperthread, some other times is a physical core. So we can talk about why do we need a full physical core, why do we need a hyperthread some of the times. And the reason is because you have two hyperthreads, two hardware threads basically per physical core. They are sharing a lot of the core resources, like level 1 cache, level 2 cache. I'm talking about the Intel architecture at this point, right? So sometimes it's actually better for performance reasons not to use the second hyperthread, just to leave one of the hyperthreads. Some other times you can enable the second hyperthread and get a performance boost, but not all the time, and it's largely due to the sharing of cache. So both of them are sharing the same L1 and L2 cache, and they can thrash each other's cache. So then it's sometimes better not to use it, especially when you have plenty of CPU cores on your CPU. So then no reason to use more threads. Some other times it's beneficial to enable that. So what do we do there is we simply run an infinite loop on each of these threads, and we poll for packet. We look, we go to the NIC, do you have packets? Give me packets. We usually ask for a burst of packets. We have like a size for that burst. We say, give me 32 packets, and we might get 32 or less packets, or even 0. We might get 17, we might get 13, we might get 32, or we might get 0 some of the time. Right, so
it's fair to say you're actually in the DPDK application at that point in the game. The while one loop really isn't in the DPDK. It's something that actually is in VPP in our input node.
exactly. So that infinite loop is part of the application. Really, it's not part of the driver. It's not part of the library. Exactly right. Yeah. So that's how the reception side works. On the transmission side, it's probably even easier. You just have your burst of packets, whatever packets you have right now, and you just push them to the NIC. You say, send me these 17 packets. And then the NIC could tell you, yes, sir, I was able to send all of them, or actually I was only able to send 13 out of those 17 packets. So then you have a choice as a user. You can drop those 4 packets that were not sent successfully, or you can retry. You can retry later to send those packets until you succeed.
So in the earlier presentation, there was a mention about the more vectors we are able to service, then we can amortize more, right? So that was one of the plus point in VPP. Now, the underlying DPDK, if it limits to 32, is there a problem, or can it go beyond 32? Thereby, VPP can efficiently amortize more than 32.
Yeah. So these are just numbers. Okay, so which is the best number? The best number is that number that gives you the best performance. So sometimes it's an empirical trial and error. Some other times it's related, and most of the times it's related to some constraints along the line, whether it's cache lines, whether it's bandwidth to access the cache memory or to access the external memory, or the PCI as well. So obviously these numbers need to be usually at a power of 2, and it's all about saving PCI bandwidth, it's saving memory bandwidth. This is what the Polmo driver is. The CPU is really just not doing that much, it's simply just conducting this whole process, which is prefetch this, prefetch that in a way that would attempt to save as much as possible the resources of the platform. Because it's not the CPU cycles which are the bottlenecks, it's not the CPU which is running too slow here. It's actually CPU is waiting most of the time for I/O, whether it's memory, whether it's PCI. So it's just the CPU is trying to be as flexible and as good as possible to save on these resources. That's the philosophy of the thing. Yeah.
Yeah, wasn't the queue size of 32 selected because it corresponds to the burst size of 32 selected because it corresponds to the queue size of the NICs?
No, actually the queues, I think typical values would be for, so NICs usually have queues, receive queues and transmit queues. This is how we work with the NICs, and I think at least for Intel NICs, the typical size for a reception queue would be like 128 descriptors, and for transmission, I think it's 512 descriptors. So I think this is what we typically use in our sample application.
It's optimized for PCI burst size then?
It's optimized. It's all about PCI, and it's all about memory. Yes.
Well,
I mean, the way it was developed, really, and Shrikant is here, and Patrick is here, Jeff is here, colleagues from Intel. I mean, you guys, sure, you use PCI bus analyzers, you use memory, bandwidth analysis tools, and this is how you develop these drivers.
It's 32 because I typed 32, and then that was pretty good. It was better than 24, and it wasn't any better than 64. So that's why it's 32. You could change it.
Yeah, and these things also change with a new NIC, with the new CPU generation. I mean, it's like a never-ending story. You can never say it has to be 32 because of some, I don't know, philosophical
let me
reasons.
try something for a second here, which is to say that when you throw in doing massively, massive amounts of real computation in the network stack, then that burst size is fine. What we literally do in VPP is we'll suck as many such bursts as we can. When we see the size drop below 32, say, okay, fine, vector, and go actually process it through the net stack, because the loop time that you've probably tuned for is almost on a max snake test, where you're doing not a heck of a lot of touching of the packet data, or you're able to in a small enough number of clocks make 32 be the effective vector size of the lap around the track. With the VPP stack, we find a vector size of around 100 is actually more effective. So what we do is we construct them by just repeatedly calling RX burst.
Yeah.
And the idea being you want one lap around the applications track, to run at the smallest vector size it can handle. And the bigger the application gets and the more it's pressuring the memory subsystem, we really don't get around the track that quickly.
Yeah, I think Dave, you already explained, like in the previous session, you gave a number of reasons why this vector processing is important. So vector, not to confuse with the vector instructions that Intel CPUs do have and other CPUs do have as well.
Well, Keith just lost a slide for tomorrow.
It's just like a vector in the sense as opposed to scalar, as opposed to just handling one packet at a time, you handle a burst of packets, an array of packets, a vector of packets.
Yep.
You work with them together. Why? Because there is a fixed cost that you can pay per packet, or you can pay for per burst of packets. And obviously, if you can divide the fixed cost to multiple people, then the cost per packet will be lower. Yeah. So then things start to work in your advantage. As Dave also said, there are limitations. You cannot do that forever. You cannot work with a burst of 1 million packets. So first of all, it will completely kill your latency, network latency, and a lot of other things. And you will need to have like huge amounts of memory, like fabulous amounts of memory on your system. But there are a lot of limitations, a lot of parameters here and there that you need to consider.
Yeah.
So is it safe to assume that the burst of the packets that DPDK processes, is it same as the vector? Or how different are those two?
Well, let me say it a different way, is that we ask the DPDK for a burst of packets. At the moment where one of two things happens, we see the burst being less than 32, we say, okay, we just clean the ring off, so we might as well take, that 32 times, n plus some constant and process them through the VPP graph. That we don't, again, we're sort of sitting over the DPDK drivers, and we work as aggressively as we can to try to clean the ring off and then say, okay, look, I know I'm not going to be back here for a while. We'll let the NIC continue to DMA, and then we'll receive bursts of whatever size we can get. 32 for the larger application. Even for an IP4 racetrack application really isn't big enough to get the maximum node drop rate you can out of the machinery. That we the other thing is if we hit VPP's maximum vector size, which is 255, we say, okay, fine, process it. But at that point, we know we're tail dropping on RX.
Yeah, but you are also right, because most of the time the burst, the vector is originates from I/O. So you read this many packets. This is your burst that you start running with. And along the way, obviously, some packets will be dropped, some packets might go left, some packets might go right. But this is your initial burst that you start running with. Yeah.
And like I say, we work aggressively to clean each RX ring as we encounter it. Then we shove the resulting vector into the graph, and out the other end, you get the law of the excluded middle is a little bit violated. You get rewrite and transmit flat drop, or or otherwise. How would you put it? You can do multiple things involving layering and caps on top of the packets, and that's the stuff that tends to get you larger vectors. Is just the amount of time it takes the VPP dispatcher to get one lap around the track.
Yeah, another thing that might be also possible, and probably not that typical, but you could go to a different vector size during the processing if you go through a queue. So if you have a queue in the middle, you might inject packets with a certain burst. You might dequeue on the other side with a different burst size. So that is true here on the ring size. It's also true here on the QoS side. Which VPP guys are not using it, and I spend.
Well, let me put my hand up and say we absolutely invite you guys who really know how that stuff works to crank it up for us. Because I mean, again, VPP is totally open. I have no, I actually have a great reaction. You guys have worked on this. I know this is one of your babies, but just by the way you were talking about it earlier, for God's sakes, crank it up for us.
Yes.
I hate to hold up a mirror and say, there's where the implementation department is. But as folks get more comfortable, listen, as I said, I spent years rolling the rock up the hill. Now it's rolling down the hill. Please just don't hit my house with it, okay?
We'll make sure we don't do that.
Well, if we can help, if whatever I know about the way this stuff's dynamics behavior, is. Be in touch. I mean, we'd love to work with people doing interesting stuff. I mean, the goal isn't to say, oh, what's mine's mine and what's yours is yours.
Yeah.
That obviously we depend critically on the DPDK community. We've really appreciated the work you guys have done. We're glad to see you folks here, and you just help us make the resulting system better.
Yeah, so that's what we plan to do, and that's also where I would actually put my priorities going forward. Like, for example, I mean, maybe let's do that. Any questions so far on this first bottom half of the screen?
This is my understanding. Correct me if I'm wrong. So my understanding about the relationship between DPDK and the VPP is that if I look into the code of DPDK, it's actually like a burst of 32. I got a 32 packaging, and if there's a DPDK code, I can see a for loop or to look at this 32 packet and process it one by one. But if I as VPP, it's kind of we get that chunk of packet and put that into vectors and the process of vector by vector. Is that the idea?
The only trick we are doing is if we get 32 packets, we ask DPDK for more.
Okay.
So we are not happy with 32. We will ask, do you have maybe a few more for us?
Right.
And if we get additional 32, we will try again.
Right.
Up to the point when we get either less than 32 packets from the DPDK, or we hit the VPP vector size, maximum vector size, which is 256.
So if you got the vector filled up, you then do the process.
Yes.
Okay.
Yes. Or if we realize that there is no more packets on the NIC. And we consider that true if we get less than 32 packets in the burst.
Okay.
Yeah, so that's probably the reason that you optimize for a certain burst size. You optimize for performance, really. This is what you want to get. So when you do have a lot of packets, you'd like to execute those packets very efficiently. When you do get less packets than usually, so for example, you get 0 packets, okay, then you might enable the interrupt mode, right? Like, okay, I'm gonna go sleep for a while until you wake me up whenever I get more packets. So that's the reason why this poll mode driver, by the way, is also transforming a bit. It's not exclusively just polling, is also interrupt. But whenever you have less than a full burst, what that tells you is that you don't have that many packets. You don't have the demand, the input traffic is not that high. So you can afford to take it a bit easier, to be less efficient. Spend more cycles per packet, be less efficient, you optimize for your full burst size. Whenever you get less than that, you can be less efficient, but that's fine because, hey, anyway, you have a big gap on your demand, so you could do that.
No, but on the other side, let's say if you are asking for, let's say your size is 100, right? You are going now piecemeal, right, to DPDK. Now each call is going to have overhead, and you are doing it in the fast path. Have you done the measurement of wish list? If when I ask, I want DPDK, if it queues everything at one stretch versus piecemeal.
Yep.
The delta in performance, do you have a feel of that?
Yeah, I mean, up to the DPDK 1.8, we are getting full frame of packets. Whatever was the number of free buffers we are giving to DPDK, we get it filled. But after the 1.8, we started getting only 32, right? So yeah, so for our specific case, it will be easier if we can tell the DPDK give us 256, than calling 5 times or 6 times the RX burst to get 256.
Hang on a sec till we can get you a mic.
So is there a time limit where you wait for your vector to fill up? Because there may be like latency involved there.
Well, the story is the VPP graph dispatcher is an eager algorithm. It pulls all the packets it can off the RX ring up to its internal vector size limit, runs them through the directed graph, and then goes back and looks for more. That it just we run around that track as aggressively as possible. We're not deadline timering anything. The things it's effectively a self-timed equilibrium.
Okay.
No. What we do is we literally say, okay, across all of the interfaces that we're looking at, grab all the packets you can, form a vector, shove it forward, and repeat until you're done. So what you get is just plain self-timed. That we go as fast as we possibly can. If that means we're getting 1 packet per vector, that packet's not going to be processed as quickly as it would if it had 100 friends.
So I guess my confusion still is that, let's say you get 32 packets, you go ask DPDK another 32,
Right.
you're getting 32. And then if it's less than 32, you stop and start processing all the packets.
Yeah, so
Now, how do you ensure that it doesn't cause tail drop that time? You can have a flurry of packets coming there. You will be processing in different cores, or how does it?
Right. Well, laying aside RSS and so on, we don't configure the RX rings as small as maybe the numbers you've been hearing. I mean, Damian, do you remember off the top? Yeah, we're using like a 4K RX ring, and we just let the hardware continue to paint memory. Now, the thing that the guys are going to the guys who really know the way the hardware works are going to say, well, yeah, and we're trying to do L2 direct deposit, and all of a sudden we're going to start having packets getting flushed out of there. It's just, the world's a mess in that level, that we try to go as quickly as we can to keep from having too many packets pile up on the RX ring, but you're running thing right to the cliff, which the cliff in VPP land, when the vector size hits maybe 160 or so, you have to breathe on it to get the vector size to go to 256, that it takes almost nothing to get it to jump. And that's just fundamentally out of gas. That the hardware can only do so much. It's not a hard. Running over Linux kernel is relatively speaking good in terms of its real-time behaviors, but it's not hard real-time. It's not something you'd find in the flight control system of a Boeing jetliner. You hope. Yeah. Where somebody types LS and all of a sudden the plane crashes. I'm being a little flip about that, but. The flight control software is not going to be as complicated as this system is in terms of its dynamic behaviors. It can't be, because otherwise, you'd be having a Boeing jetliner on your house all the time.
Yeah.
Can you please comment on how DPDIO is interacting with DPDK?
Yeah, DDIO, that stands for Direct Data I/O, I think. So what that is a hardware feature of the Intel CPUs. So basically, part of the last level cache is allocated to NICs, to whatever device sits on the PCI bus. So some of the ways of the cache, a certain number of ways of the cache is allocated exclusively for the usage of that device over there. So what that means for NICs, it means that packets will actually go to the last level cache. And if you are quick enough to process them, and quick enough doesn't have to be super fast, but reasonably quick enough to process them, you don't need to read those packets from external memory. You read them from cache. So that's one of the critical hardware features that enabled performance improvements over time.
If I want to use that feature, do I need to do any configuration or it is?
No, that comes by default enabled.
So do I have a means of allocating more LD cache for this packet processing?
I don't think you can do that on the current generation of CPUs. So maybe going forward, things might change.
Do I have to use Intel need for DPDIO?
No, because it's simply whatever device sits on those PCI lanes. It could actually be a chipset as well, right?
You,
If I have multiple PCI devices, can I allocate this LD cache only for the network device? So you have multiple devices sitting on the PCI bus, but I want to allocate my LD cache only for network. Can I do that?
I'm not aware of that right now.
you have, as part of DPDK, I'm here.
Okay.
As part of DPDK, you have a sample program or something which says wire speed 40 gig, you are able to do it with one core and things like that. Is it a sample program, the red box there, DPDK sample app, or is it part of the DPDK itself, like the layer processing, the layer 3 processing?
I'm not sure I got the question. So as part of that, what are you looking for in that program guide?
DPDK claims that they can do routing of packets, including the layer 3 lookup and all that, at like 40 gig or so, with just one core, as an example of how DPDK performs. And I'm wondering, I'm trying to place it in this picture, where that program is. Is it part of the sample apps, or is it part of the framework of DPDK itself, like a layer 3 lookup and things like that?
Yeah, I don't think it's a library. I think it's a sample application, and it could be different. I mean, that's like, I think what we have, it's a sample application that implements the RFC. I don't remember the RFC number. Is it
4544 is the performance test, the latency
Yes.
performance test, but the checks are different. 1812 or
Yeah, there is an RFC number that I don't have
Okay.
right now, which states how L3 forwarding, how routing should be done.
Okay.
So that's
And-
what the sample application implements. Obviously, in VPP, which is a true network stack, you have more counters, you have more functionality,
Right.
more
So
tables.
I'm trying to place it in the picture. So the VPP will be one of the sample apps on top of
VPP
DPDK.
is basically a user of those libraries.
Yeah,
User of the DPDK library
Exactly,
and build it
exactly.
on top of it.
Yeah, the application
yeah,
stitches up together all these libraries.
Let me try for a sec. I mean, VPP is somewhat of a sample app on a considerable dose of steroids. It's just that is exactly thematically what it does. Is it
Okay.
can, what would you say about it? We call EAL and it with a bunch of arguments that we've scratched our heads and figured out, okay, we kind of want to run it this way, whitelist, blacklist. I mean, we use the EAL, the EAL configuration facilities extensively. We use all of the, as folks have been saying, we used all of the libraries and essentially all of the PMDs. The things that we haven't done so much are exactly as you were mentioning earlier. We're not using the QoS scheduler, and why is that? Well, I mean, I have 10. He's got 10. Keith has got 10, and he's just sort of, he's new to the party, and the number of folks who are currently working on VPP within Cisco is actually is way small relative to the number of people that work on the DPDK. As it turns out.
Okay. So
You might be surprised.
Well, I mean, it's the old how many people work at your favorite company name on, on a good day, about half. Well, that's another problem you can't get away from.
So the aim is to align accordingly to make sure that DPDK and VPP, they complement each other.
Well,
Right?
yeah.
Because initially you mentioned
Yes.
about why VPP is not not using some parts of DPDK and all that. I know you mentioned about QoS.
Let me do 2 sentences of history. One thing to say is that I really did start working on this stuff a dozen years ago, and if you want, I can send out pointers to even a patent that was applied for in 2004 that mentions some of the same techniques. And we've made decisions to say, okay, it's great for the networking industry to advance, but you ask yourself, well, why aren't certain things more intimately tied to the DPDK? It's that what we're running today predates it. That IPFib lookup technology, you could easily imagine that the DPDK has a better way of doing it.
So it's one of the challenges, going forward, that we put integrate the two things better for the benefit of both, really.
And
so, for example, like on the classification side, we do have an ACL library. You guys have an ACL library. We do have hash tables. You guys have a classifier. We do have an LPM table. You guys have your FIB.
Well, and
so one of the things that I would like to do going forward is try to understand your code and understand, okay, what's missing from our side, or is there anything that we need to push into your side to make it better? That's something that we need to collaborate.
Absolutely. I'll tell you a little story, which is that reworking, picking up a different lookup method in the IP4 FIB is. It's surprisingly easy. I was able to take an open-sourced PopTry implementation and crank it up in one day, and that's the kind of level of effort. VPP, say what you will about it, is pretty nicely orthogonalized in being able to use different underlying mechanisms to do the same thing. And it's everybody in this room and all your friends' party now. For God's sakes.
Yes.
I'm here to be a little bit of a consultant and say, if you do it this way, it might work better, but I don't have an agenda about it.
I've got a question. So I can use either, but I am probably the only non-coder in the room. I'm the user. I would like to use whatever is faster.
Exactly right. So I'm not saying, none of us is saying that one is good and the other one is bad. What I think we are saying is we need to understand what feature each of these components has, what gaps it has, and what performance it has. So then combine what is good from both worlds so that we can create a better one. That's the whole purpose.
So let's test.
It's not to say exactly. So testing is the one that should decide. Technical arguments and technical numbers should decide. It's not like preferences.
Perfect.
We don't need to go into a religious battle here. It makes absolutely no sense. So this is a technical, like getting the best of both technical worlds. Really.
These are both libraries or sets of libraries. One has a lot more production time on it than the other, but it's a collection of things you can use to build interesting apps.
That's what we need to find out. This is why we met today, so that we start learning. I'm here to learn about how VPP works and what's in there. It won't finish in the next 3 days. It will continue for quite some time, I'm sure. So more than happy to do that and contribute, hopefully.
I have a question. There's so many questions, it's difficult for me to ask my question, okay? My question is, I want to understand the data flow, because Dave mentioned about DMA from NIC to memory, right? So when you do polling, okay, where do you pull from? You're not pulling from NIC, right? Because that's going through I/O. It's going to be very slow, right?
No, you are pulling from the NIC queues. So
okay, which is a memory.
The NIC queues are in memory. So the hardware does its a job from getting bits from the wire, creating bytes, creating packets, DMAing them into memory, and writing the descriptor into the queue as well.
Okay.
Software does its job in creating the memory pools, polling from those rings, refilling buffers with the empty buffers in the ring, and getting those buffers that have packets.
So
the interface between hardware and software is actually those queues that are in memory, which are basically data structures.
Right, and they are kernel memory or user memory?
They are user memory.
Okay, so you direct your DMA data from the NIC directly into the user memories.
No, the NIC will DMA data.
The NIC will send data wherever you tell it.
Yep.
Yeah.
Yeah.
Subject to protection.
Yeah, and
Yeah, but I don't think user memories are virtualized memory.
No, you're right as well. I mean,
so it
CPU
has
is
to be
also
a
DMA
physical.
will also
Okay.
read that memory, look into the packet headers, analyze packet headers, look in the packet depending on your application. Might be encryption, a software library, it might be compression, it might be whatever packet.
Okay.
So
It's process memory that's mapped so that it can be seen from the hardware. So you've got process memory, you've mapped it, and you have a physical address associated with it that's then the hardware side sees it. So when you set up your ring buffers, your ring descriptors, they have the physical side address and you have the virtual side address. So when things are written, you see it from the virtual side, the hardware sees it from physical side, just like it would work in the kernel, but it's user space, it's process space memory, it's not kernel memory.
So this is just a driver. If you are familiar with the kernel architecture of the driver, this one is not that different, okay? It still works using the same rules because those rules are set in stone by the hardware. Hardware dictates the specification, will tell you which those rules are. So we have to play it in the same way. It's still software. The difference is that, okay, this software is in user space. We need to work in polling mode. There are no interrupts here, or not as many interrupts.
So you're polling from the memories.
Yes, but it's still reading memory queues, reading data structures. This is what it is.
And there is another important point here, and that is why we need the huge pages, which you didn't mention before, and that is that physical hardware can know only about physical address. And if your page size is only 4K, your descriptor or even the packet, if you are getting the jumbo packets, can be bigger than 4K. And if you allocate for the memory from the normal memory, it can easily happen that they are not continuous. So that's why we need huge pages to be sure that the memory, we have the exact mapping between the physical and user memory. And that's why we have this huge pages requirement in VPP and in DPDK at all.
Yes.
So when you talk about interrupt, okay, you're talking about NIC interrupt?
Yes, it's a NIC interrupt that somehow gets to the software in user space, wakes up the process in user space.
Right, but if you take the NIC interrupt, right, and then right there, you know the. No, I'm okay. No, that's fine.
Yeah,
Okay,
we're going to have another session on DPDK later on Thursday.
Yes.
With Damien,
Yeah,
we're going to go through more of the performance side of things, the threading.
Yeah, I mean, you can also have a kernel driver that works in polling mode.
Yeah, maybe another
disable
point
interrupts.
to mention here. We can use all these kernel drivers in VPP. So typically we still prefer IGB.io. My understanding is that the only difference between the UIO PCI generic, which is a kernel which is provided with Linux kernel, and IGB.io, which is a DPDK driver, is that IGB.io supports interrupts. Beside that, they should be the same, right?
Actually, that driver came from FreeBSD, if you look at it.
Yeah. Okay. And we are fine with working with any of them. At the moment when we will enable the interrupt mode, we will probably need to use IGB.io because there is no such support in the UIO PCI generic.
how many of the poll mode drivers actually do interrupts at this point in the game, or will soon? Because it's not going to be all of them.
Few of them.
I actually don't know.
I was looking at a few weeks ago. I think in the latest DPDK release, all Intel drivers are now interrupt, but other vendors don't have it, if I remember correctly.
It's really only for the link state.
It's also for power save. Right?
Okay, so yeah, I think we also have other libraries like fragmentation for IPv4, IPv6 fragmentation and reassembly. There is a similar component in VPP as well that is part of the stack, probably better integrated to the stack that VPP is, the network stack that VPP actually is. We have the quality of service libraries. I think you guys, as I looked, you have like some metering code for SRTCM, TRTCM for the coloring algorithms. I actually didn't look in detail on that code.
The policer code is pretty good. It does it's single dual leaky buffer leaky buffer bucket. Yeah. Sorry, for my brain is in the wrong time zone. I know that excuse is lame because many folks have traveled way more time zones than I have, but I'll use the excuse I'm older than a good fraction of the room. At any rate, the story is the policers that are in VPP now are not bad. They're really pretty fast. They were done by a guy within Cisco who's quite expert at it. On the other hand, they're at best lightly used at this point in the game, and swapping in another library would be easy.
Yeah.
So
I mean, they are at the end of the day, they are standards, RFCs,
Yep.
and API cannot be that different, so on and so forth. The scheduler block is something that I spent like 1 year of my life.
yeah, I don't doubt it. I have great respect for getting that problem right. It's not.
Yeah, I mean,
It's a hard one.
initially it was like one of those impossible problems that we tried to look at,
Yeah.
and we managed to make quite a good progress on most of the typical algorithms that you would see for scheduling. I mean, what we have right now, it's like a 5-level hierarchy. It simply can be used to prioritize traffic that needs to be sent out on an output port. You have a limit on the number of packets that you can send out. It's like the limit, the physical limit of the port plus whatever other constraints are part of the SLA, or the service level agreement at every node. You have traffic classes, so some packets are like voice packets, video packets. You guys know better than me this part of the story. They have different requirements on the delay and delay variation, latency and jitter. Then best effort traffic, which is most of the traffic, where congestion usually is. Usually this is done on the hardware side, so there is like there are a few tricky things here. We do have thousands of queues that we organize in a hierarchy. Like the interface is in-queue packets on one side, D-queue packets on the other side. The in-queue packets are in queues based on the reception, the reception functionality as the packets come in. The packets are dequeued based on the requirements from the NIC whenever NIC needs packets and according to the SLAs, and which includes like whatever limits you have on different levels in the hierarchy and priorities for different traffic classes. One keynote here is that right now I do have a challenge to integrate this into VPP, because usually this is done on the hardware side. So you could look at this block like the last stage before transmission. You could look at it as part of the NIC itself. So think about this case. I should probably draw a couple of diagrams here. The thing is, the way it works in the DPDK, at least at this point, is like you create an object, a scheduling object, which is like a big reservoir of packets, and for each of the output ports that have to implement this requirement. So in other words, whenever you have a routing stage that packet come in on whichever input port they are received, but then packets can be sent out on any output port. So looking at the VPP model where you have like these workers that are kind of monolithic and they all need to implement the same things, and they don't communicate. This is a problem at this point that we probably need to solve sooner rather than later, because packets that are routed to the same output port, they need to go to this worker that would implement this in software. So there is a communication of packets that need to happen due to the way this works. So that's one of the things to
That's
keep
not
in the back
actually.
of
That's
the mind.
not actually. There's actually a really good place to do that. That each output interface has, has prior to going anywhere near the driver, it has an output. It has an output node and a TX node. The output node would be a really great place to say, oh yeah, well we're doing queuing today. Bang, put it where it needs to go.
Yeah.
And
So it's a good place to start from.
I wouldn't at all preclude running the output scheduler and the physical TX just in a thread that's running, one to n threads that are running pure DPDK code and nothing else.
Yeah.
But that's also pretty easy to arrange.
Yeah.
But
Maybe a few words about the packet framework, which is my baby.
Doing that. So you're saying that's a problem to be solved, you said, right? You were mentioning that it needs to. This is one problem which needs to be addressed. So I'm wondering if we do not address right now, what's the
It
issue?
should be very difficult to implement like a software, to have a software implementation of the hierarchical scheduler. Because it's kind of attached to the output port,
Yeah.
it's part of the output pipeline of the code rather than the reception, the input pipeline.
Yeah.
Yeah.
And it's a known hard problem to get
Yes.
really right. I mean, folks at Cisco have worked on it for, have worked on, on output scheduling problems for decades. And usually what you tell people are, oh, policers, there, if you need QoS and you can get by with policing, if that really makes the requirements, just run policers because they're way fast and they're not near as hard.
Yeah.
And they don't have the, here's the gigantic bucket of packets and here's trying to schedule the link accurately, which is really the toughest part of it. I mean, I'm sorry for, jumping in there,
Yes.
but I fool with the problem and it's a known hard one.
Yeah.
So if I could quickly comment. So I agree with Dave, but still, from what I understand from documentation on DPDK, DPDK implements actually 5 levels of hierarchical scheduler, correct?
Yes.
What documentation doesn't state is whether it supports priority queuing and priority propagation. Can you comment?
Priority queuing.
Magic, that's a real good one for over a beer.
Okay,
Yes.
so let's do
So-
over a beer, but if we could leverage this code to get HQoS with VPP, that would be awesome. Thanks.
Yeah, sure. Yeah, so pretty much all the algorithms that are part of, that are traditionally part of hierarchical scheduling, like token bucket, strict priority, with whatever limits you need to have, weights attached to the queues, everything works brilliantly in software. The only thing that doesn't work that well in software is weighted fair queuing. The fair queuing part for a large number of queues. Because usually the way you do that is like you use an array of comparators in hardware. You just need to detect which is the next guy to send, the next guy to send based on the history. And without having some special instructions or without having hardware acceleration, it's really hard to do that in software. I actually didn't find a way to do it. We do have weighted fair queuing for just 4 queues at the bottom of the hierarchy, which are 4 queues within a traffic class. But that's just a detail. You don't need to remember that at this point. So you can do weighted fair queuing, but for a small number of queues. Weighted fair queuing for a large number of queues is very difficult actually to be implemented in software without hardware assistance.
The key thing we want to get out of this is that there's a whole lot of facilities coming into DPDK. We could leverage it. David and I, I'm sure Damien have already talked about, there's, as more and more facilities become available in DPDK, being able to directly inject into internal graph nodes your packets and bypass some of the older input nodes would be eventually a good thing to do. And there's certainly a lot of use cases for it. So definitely not precluding it. We're already going on how can we do that. NSH is another example.
It's just throwing ideas. I mean, what I'm trying to do here is like throw ideas about things that we could do in the future. It's not like I'm saying we need to do that. We might talk and find a better way to do it. So it's
I'm just actually trying to give you a little nudge
future.
onto the next slide, mate. If
Yeah.
you could. TikTok.
No, I
There you go.
think we're done. I mean, I just wanted to close on this slide. The packet framework side, this is one of the things that is basically like a structure to build applications. It's probably one of the things that will never be picked up by VPP because VPP is like a stack which has its own structure, its own way to add features in a modular way. One of the things that I used this packet framework tool for was to build an edge router, and this is part of DPDK actually. It's like the way it works is the way this tool works is really you hook up some blocks together. You can create run to completion pipelines or hybrid applications. You just throw things that are called pipeline on different CPU cores. We built an edge router, and it's part of DPDK, simply like a configuration file that implements an application. Okay, this is one of the things that maybe we can think about how to do in VPP, how to transition for a let's say a static model of just workers that all are implementing the same work, that maybe to let's say a finer grained parallelism here and modularity where we can actually break these workers into smaller pieces. So that's something to consider for the future. I think you guys are right at this point on given a number of challenges in the CPU, like core-to-core transfers, which we can talk about in the next session on Wednesday, probably run to completion is the best that you can get at this point. What we can actually see with this edge router and other applications is that sometimes, and most of the times actually, it is actually beneficial, even on the current generation of CPUs, to have small pipelines. Think about this case where you have the two hyperthreads of the same physical core that are communicating with each other. And one hyperthread is doing, let's say, some blocks. The other hyperthread is doing the other blocks of this worker that you guys have right now. It's a small pipeline. You don't have to go through a last level cache in order to send packets from A to B. It's still a pipeline, and it's like you can create this small pipeline and that you can replicate on different cores. So you can create a lot of topologies, and going forward with the next features from Intel CPUs and probably from other CPUs, we can actually see these hybrid and pipeline models getting traction. So for the future, for the years to come, it's something that it might be beneficial to think how we can implement this or structure this, make this available in VPP as well. Just another idea to think about. So I'm done. I mean, depends on how much time we do have. Like, if people have more questions, whatever you guys want to have right now.
Yep,
I was just going to give a wrap up, but
my suggestion is if you could give an update on the NIC side, what can be done in the hardware, or what kind of hardware assist is available or going to be available, and that will give us a area of focus on the software side to take advantage of those. Because like now we have 40 gig, 412 and all that. We have 100 gig in pipeline, and maybe multi-100 gig coming in. The hardware assist, like pre-populating the cache, and whether there will be any dedicated cache for such devices, or any, or in L3 outside the cache, outside the processor, whatever it is.
Yeah, I'm not sure what exactly you mean by pre-populating the cache. I mean, usually this is like packets that come and go, and it's like millions of them every second. That would just thrash the cache. I mean, it's something that you need to work with, live with. Obviously, you have data structures that are longer lived, like flow tables, routing tables, so on and so forth, that need to stay there.
For example, as Dave mentioned, how many packets they're just blindly polling 32 at a time. Instead, if they could give you a number wherein you could populate and prompt, that would be an easy assist rather than keep on polling to find out whether there's more or whatever. As a simple example. If I say that I'm looking for 256, and here is the timer, you interrupt me. If you don't have, interrupt me immediately. If you don't have any other packets, you have only received like 56 packets, and you see a pause on the line, immediately interrupt, saying that I have a 56.
Yeah, so these are things that I mean, there is a lot of prototyping work at this point. We try to optimize this handshake between hardware and software. We try to add more features on the NIC side. Probably the other vendors are doing the same.
Yeah, this is one of those places where, for instance, a lot of the effort in the Intel NICs appears to be adding de-encapsulation for things like VXLAN or data center bridging, that kind of thing. A lot of the new NICs have those hardware acceleration features, somewhat at the expense of pure speed, right? What other NIC vendors do, who knows, right? Somebody's going to find an opportunity in the market and go try to construct a solution and own the market, right?
Yeah, I mean, basically you are touching the point of hardware offloads, what the NIC can do for you, right, for the software to optimize. So one of the places where NIC can help, and it helps immensely, is to help with this load balancing of traffic like this traffic steering from ports from physical NICs to CPU cores. So the way we do that is simply we try to, we have these filtering features in the NIC that are a never-ending story, which basically regulate how packets could be placed in when using several queues, rather than just put all the packets in one queue, split the traffic according to whatever criteria, and put different packets to different queues. So, for example, if you have the notion of a flow and your flow is the diffser 5 tuple, right? You could look at each 5 tuple as a different flow, and you would like to put different flows to different queues, right? So that's one of the fundamental issues or whatever problems that the NIC can help with, right? And there are a lot of things there. Some of them have limitations. Some of them are better than the others. Different features depending on the vendor side, how you can actually do that, how you can help with traffic steering, with load balancing. So that's one of the key features. On the Intel NIC side, I think we have a feature called RSS, which is basically computing a hash over the packet, the flow key that you kind of register. You say, okay, these packets, look at them as IPv4 packets or IPv6 packets, TCP, UDP, SCTP. Extract these fields from the packet and apply a hashing function, create a signature, a hash digest, and use that to compute the ID of the queue where the packet needs to be put. So that's called RSS receive side scaling, and it's kind of ported from one NIC generation to the other. I think the latest NIC has more facilities on packet fields that you can pick to build up that key. There is another feature which, as far as I know, which we call flow director. I think Mellanox NIC also has that feature. I think they call it in a different way, where you kind of build a database of filters, and you kind of say, here for this 5 tuple, put these packets in this exact queue. So you are actually able to configure the queue where these packets will go, rather than having the previous feature of RSS, which is a bit inflexible in the sense that you always compute a hash, and that hash you cannot change it. So whatever number is the result, that is the destination queue. Yeah. For this other feature called flow director, you can actually register the destination queue for each of these flows. And now this flow can also can be an exact match 5 tuple, or it can also have wildcards. You could maybe wildcard some bits from IP source or IP destination. So it can actually be a higher level, coarser grained flow that you can put in certain queue. So these are like two typical features, NIC features that can be used to bifurcate the traffic in an intelligent way. So then you bifurcate it into multiple queues, and then on the other side of those queues, you have different CPU cores. This is how you distribute traffic. And this is actually one of the tough problems that is quite difficult to fix in software, because fixing it in software will take you at least one CPU core to implement that load balancing algorithm. Not to mention that you are limited by whatever one CPU core can do, because this type of feature usually needs an arbiter. An arbiter needs to, that arbiter needs to see all the traffic and direct the traffic on the other side. So then it's maybe a bit more difficult to use two different cores to synchronize between each other to kind of implement an arbiter. So you are typically limited by whatever bandwidth, whatever throughput of load balancing one CPU core can do. So this is where NIC helps, and probably could help a bit more going forward.
I want to ask a quick question for the PPP folks. Could you please why you guys decide to use DPDK for VPP other than other technology?
That's actually a simple, about 1.5 sentence.
There wasn't any other.
Well, for the longest time, we had our own device driver model, and given the number of people, that could possibly be involved, writing a device driver is damned hard work. I mean, props to folks that have done it. I've certainly built device drivers. You guys have built them, and we don't have the Intel Red Book stuff. We don't have the really the intimate knowledge of the hardware to get a device driver, just to get that layer right. And once you've lost the performance in a device driver, it's gone. You can never get it back. I mean, you can write the most brilliant stack you want, but if you're getting one packet every 5 minutes because your device driver sucks, game over. Game over, Beethoven. It is really hard to get this right, and the DPDK drivers are by far and away the best. Now, can I put my hand up and whine a little bit for a second about, please guys, when you write a poll mode driver, do not do the link up down stuff in a way where if you shut down a link on a particular interface or bring up a particular interface, some unrelated interface is not going to see the CPU again for about a week. That they're spin waiting in one of those device drivers is the bane of my existence. I get a call from an internal customer who's saying, hey, I'm getting all these damn BFD flaps. So why is that? BFD, by the way, you have 50 milliseconds. There are places in some of the interface up paths that'll spin for more than 50 mils, and you can't do that in a real networking stack. So we stood on our head to whistle Dixie, but that's the kind of thing that the device drivers maybe aren't perfect at. But on the other hand, in terms of getting the ring bashing right, getting the interface to what I've been calling L2 direct deposit, but just simply to push data into a place in the cache hierarchy. That stuff is a ton of work, and it's really hard to get it not to have stupid bugs that happen once a week when you're on night call. That's why we use the DPDK, because they're damn fine. They're damn fine device drivers.
Have you considered other corner bypass technology like NetMap or other things?
NetMap.
Oh, NetMap. Yeah,
we looked at NetMap.
Yeah, actually, we have the NetMap in the VPP. So some time ago, one of our colleagues investigated this. He created the NetMap stuff. It's actually in the VPP code base. Right now, it's disabled, because we don't have users who are using it. But if somebody wants to re-enable it and use it, first it will require some care and attention to really make it working and then it can be enabled. So there is no religion about it. It's there.
Yeah. Well, here's the thing about NetMap, and this comes directly from Luigi, so I'm quoting the author. It will never be faster than DPDK. And he said that. But it is an easier programming model.
Yeah, well, the main issue with NetMap, as far as I know, is I don't know what was happening the last few months with NetMap, but at that time, it was the way that it's not going to the Linux kernel. So it's right now it's a kind of patch which is not stable. I had issues to really.
The Linux kernel guys aren't taking any of this user space stuff.
Yeah.
Right. At all.
Yeah. But this is something we cannot fight.
There is another platform.
Yeah. I mean, if somebody wants to put this into the Linux kernel and make it usable and stable, we don't have anything against it.
Well, it will never upstream.
Yeah.
They will not take it, just like they won't take UIO.
Yeah.
Right.
Yeah, I know. I mean.
But there is another platform.
Yeah.
That DPDK is supported on.
Yeah, I know.
Okay.
By the way, I am committer of that platform.
What platform is that? Which are you referring to?
It's a FreeBSD, right?
Yes.
Yeah.
Yeah.
I'm FreeBSD committer, by the way.
Okay.
Actually, ex-FreeBSD. I guess they
they
removed me because of inactivity, but
Hey, you can come back.
yeah.
Well.
Are we done? Do we want to do more stuff now?
I don't know. You told me, dude.
I wanted maybe to touch one more thing regarding the DPDK about the integration with VPP. So what they already mentioned about this issue we had with up-down stuff, and a few more things which we have. We actually maintaining the set of patches which we are applying on the top of the DPDK. So if you take a look into the VPP source code, you will see the directory DPDK. Inside that one, you will see the DPDK version number _ patches. So the story is that we are trying to upstream as much as we can. Usually what happens that after the DPDK release, there are some patches, some issues, some fixes. Some of them coming from the Cisco folks and the INIC stuff, but also we have a few of them which are not related to Cisco stuff. One of them is patch which allows us to avoid these slips in the admin up-down. Another important one is about the structure of the MBUF header, because we noticed that there is a significant performance issue because the structure of the MBUF now contains the pointer to the next MBUF and
in the second
cache line. And because of that, we noticed like it was like 10% drop on the performance, right, Dave? Do you remember?
It was a fairly significant hit. Now realize that we generally don't run in fast mode. We generally run with jumbo frames enabled. Yeah. In fact, you can one of the things we'll see perhaps when we get to talking about DPDK command line configuration, you can feed VPP, which then turns into something is there's a DPDK no multi-seg guy that says, okay, single buffer chunks only, please. But we don't normally run that way because it's quite common for people to want to change interface MTUs with the box up and, except on the Cisco VIC. Oh my goodness. Don't get me started about that piece of hardware and the guys that did this. I mean, people will walk up to a router and they say one of the first things you want to do is change the MTU, and if that all of a sudden causes you to have to reboot it, especially if it's a big x86 server platform that takes 10 minutes to boot, somebody wants to kill you, and it's like. Pax Vobiscum, we just...
That's great feedback, by the way.
Yeah.
Thank you.
Yeah, so in general, we have the set of patches. We are trying to maintain the state that they are not mandatory. So if you try to compile VPP with the external build of DPDK, it should work. It works now.
Yeah.
If you want to really run the performance testing, we really suggest that you use those patches, at least those two patches which I mentioned before.
Or if you're testing on the Cisco VIC, for God's sakes, the performance tunes. Those guys are going to upstream that stuff. But the one other thing to say is that somebody very helpfully pointed out the RTM buff private data area, which is, I'm going to get into a long discussion of VPP buffer metadata. And one of the things we do is we make the VPP buffer metadata, tangent to the DPDK header. Well, there's not really, doing sort of a one of these. Well, now it's tangent by being embedded as private data works perfectly fine, and you still end up with the, the right alignment of the stars to see the DMA buffers. And if we can resolve a couple of the other ones, we should be able to really run properly on the upstream shared library. We want to get there because clearly, it'd be great to be able to say to people rather than downloading the PDK from, in source form, compiling it all the time. There's a whole set of people who just aren't interested in that activity. I mean, myself included, if I'm not doing performance testing, to be honest. And
Ed says we got to get this up in the distros. We got to get this up in distros. But those are the big issues that are going to affect getting it into the distros. Is using off-the-shelf. As developed DPDK, along with what upstream is doing, so that we don't, if we're applying special patches, it will create problems like for people that are using,
But even bigger problem I see that if you are going to upstream such stuff, I didn't find a way to easily basically have the binaries for different microarchitectures, and that really matters in this case. So. I mean, if you compile the DPDK to run on every single x86 platform, it will not use AVX instructions. It will not use any advanced stuff, and of course the performance will be much lower. And on the other side, if you create the AVX2 optimized binary, it will just sigil on the old hardware. So I really don't see a good solution to have the both optimized and working binaries in the distros.
Yeah, we end up. You don't want to be pushing Nehalem or better binaries onto a machine that's capable of of using the real instructions more than you have to, for sure. What do the upstreamed RPMs or DEBs look like in terms of the DPDK shared library? Are they compiled to really compiled to almost Nehalem or better? Does anybody know?
Well, I'll only speak for what the COPRA 2.5.0 OVS it's coupled with DPDK 2.2.0, and the only patches in there, is off the top of my head, are just basically to support stuff that we know is coming upstream. For example, like a multi-queue for vhost user. And
Where'd Burns go?
No, you're fine.
Oh no, Keith's lost. Anybody seen Burns lately?
He just told me that he needs to go out for something.
Oh,
but we are done, right? I mean.
Yeah, the more general questions. We don't want to keep everybody here, wear you out completely today, and then not have the steam to go through the next 3 days worth. So
one question, I was listening to some of the videos where
okay, well get on, Keith. You drive. You're the big guy here.
Yeah. So with that, we're going to wrap. A couple of things I wanted to clarify that came as feedback on the break. First thing will be the presentations that we did. I'm going to make sure they get up on the wiki. Would have been half an hour ago, but time got away from us, which is great. Good discussion, but some of the feedback was I probably went through some of the scripting stuff a bit quick, and there was some confusion over what do we need to do, why is this here, more the point, where's this freaking event, why isn't it under VPP, why isn't it under just general FIDO events, it's a VPP thing, no worries. Here is where I'm going to put the content. So I'm going to put a PDF of the presentations that we've done so far up there, so you'll be able to grab them and get all the links and things like that. But to make it very clear though, do you need to run Docker? No. That was just a demo that Nikos did, that he's done before, and we wanted, give you an opportunity to say, look, this isn't just arm waving, you have real workloads, and here's how we do things. And because he's done that, and I happen to use net namespaces to develop with because it's expedient, we combine the two. Sorry, that caused some confusion. You only need to have the scripts, the net namespace scripts, the config scripts, and I'd recommend the GDB and init stuff. They'll all be on the slides. I'll yank the URLs out and put them, again, explicitly. These are the things you need. Because it's important, and I confused you guys, and that's my fault, and I apologize. So we'll clear that up. So starting tomorrow, have all those scripts, and life goes on. What else did I forget? Presentations are going to be posted. 8:15, try and be here-ish. Breakfast is 8:30. We'll be starting at 9 sharp. So Dave Ward will be here. And so, as you can imagine, he's a rather busy person. For those who don't know, he's the CTAO of Cisco. So he's going to be here at 9 sharp and then moving on. So it's not, we don't have the wiggle room of kind of being 10 minutes late and stuff like that. So please, tomorrow is the day you probably want to really be on time. The rest of the time, whatever, it's your time. But tomorrow, be here. So 8:15, 8:30 brekkie, 9 o'clock kickoff. Then a little bit more arm waving around my perception of data plane programming. Not a lot of stuff. Just some of my experience, dicking around with networks and how I see IP and what it means to data plane networking from my perspective is it's more than just taking a bunch of bits, slapping on a template, and going, ta-da, I'm RFC compliant. There's some heuristics involved. So we'll go through that, then it's straight into the code. So be prepared. First thing we're going to do, I'm not going to go through the debugger and go, hey, watch me go through the debugger, isn't it magical? I expect you guys to put down the skeleton. You don't have to run Emacs. I've published a tarball, which I will also publish on the wiki tonight, so everyone can get it. That's going to be the graph node that we're going to be using. So that's where we're going to start. If you don't have that graph node installed, when we go through the debugger, you're going to go, what the fuck, why aren't the counters going up? Why isn't this plugin loaded? Because you don't have a plugin to load in order for the counters to go up. That's what the graph node's for. So it's very important you get that done. Can't emphasize that strongly enough. So thank you all very much for making the time to be here. Thank you, Christian, as well. That was a very good session. Really appreciate it.
Yeah.
I know you only wanted half an hour, but that was awesome. And thank you all for all the questions. And please, again, Vagrant. I think Vagrant has its pluses and minuses. The network here sucks. If you're in a hotel tonight where you've got your own internet connection, get the Vagrant thing installed, because we have a consistent platform we can all iterate with, and then I'll know what you're talking about.
Yeah.
Right? Thank you again.
Thanks, guys.
Look forward to seeing you tomorrow.
Thanks, Keith. Good job, man.